This is a digital signal processing project. Let's show what I have here. I have the Pico W. I have a red wire connected in the 3.3 volt terminal, a black wire in the ground terminal, and a blue wire at ADC0. This is all connected to a breadboard. The other side, we have the blue wire, black wire, and red wire. We have a capacitor connected between the blue and black wires, so ADC0 and ground to prevent shorting, and we have the microphone. A fairly simple circuit design. So if we're below the noise threshold, the plot in millivolts over time looks something like this. It's not particularly informative. However, when we play a frequency into the microphone, it should become much more clear. So I will demonstrate by playing an 800 Hertz tone into the microphone and show you what the graph looks like. Warning in advance, it is fairly loud, so I warn you to please turn your volume down. I'll start this in 5, 4, 3, 2, 1. So my computer isn't quite loud enough, but we can see that the waveform has changed. So clearly we have 8 cycles now that are much easier to distinguish. The amplitude is a bit less than the expected 1000 millivolts, but that's because the computer I'm using is a bit soft. So I tried it with a louder source like this phone, but I have to use it for filming. And the plot would have a higher amplitude. It would be more around 1000. Okay, let me discuss FFT and power calculation. So what I have here is FFT real and FFT imaginary. That's what's being printed in these first two lines here, these two. And on the bottom line, this thing here, that's supposed to be the corresponding power. So just to show, I have about 837 and I have about 1423. And the formula is FFT real squared plus FFT imaginary squared divided by number of measurements should be the power. And to show that it's reasonable, here I punched it into a calculator and roughly about 5,323, 5,326, so it checks out. And here was the code that I used to get the approximate noise level. So we have the noise time, noise frequency as is defined in the instruction. I have it basically take an average of noise time and noise frequency because they're very similar. And append this to a list called noise history. And then I would have it print some noise history, lower length noise history, so about average noise over time when it takes a number of samples, and it finds the average of those samples roughly, and I got that to be about 65,800 square millivolts. Now I will move on to the last phase, so that will be demonstrating the different frequencies. So I'll start with, I believe, 400, 800, 1600, and 3200 Hertz. I warn you, this will be fairly loud, so I will give a little time warning. Go turn down your volume, please. I'll start this in 5, 4, 3, 2, 1. Okay, so 400 Hertz. So its best reading is about 397 Hertz. Occasionally, and I was not able to figure the reason why, it tends to read a little bit lower than it should. It seems to happen every other sample. However, we can take the 397 hertz measurement as fairly accurate because it's just 3 less than 400 hertz. I'll try 800 hertz next. So again, it gets it wrong sometimes, but the best measurement that it gets, the closest one, is about 794 hertz, which is again within a reasonable agreement to 800 hertz. Next, let's try 1600 hertz. So it often doesn't hear it, but the best measurement, that one that appeared on screen, was about 1588 hertz. So again, the frequency that's being played is 1600 hertz, so 1588 is fairly reasonable. And last we have 3200 hertz. So it would seem about 3134 hertz was the best we could get. A little bit lower than expected, but still kind of close to 3200 hertz. It seems like the error increases with higher frequency. But this concludes the demonstration of the circuit. Thank you very much.